Hi, my name is Mas Atira Muhammad Isfan.
My name is Hun Ken Tiong.
My name is Zainal Amran Hashim Bezuna Abidin.
My name is Shahrul Hilmi Palahuddin.
My name is MD Azizul Haq.
I'm Aina Jihabindi Abdul Halim and we are from Group 12. We'll present about Gauss's law. So without wasting our time, let's get started. The Gauss law was first formulated by Joseph Lacrance in 1773, followed by Carl Friedrich Gauss in 1835. Let's start with definition of Gauss law. Gauss' law states that the electric flux through a closed surface is proportional to the total charge enclosed by the surface. A closed surface in this case is just the surface of any shape that completely encloses a charge, like a sphere or any other three-dimensional shape, and electric flux is a measure of the electric fields that pass through a given area. Gauss' law tells us that in nature there are such things as positive and negative electric charge, and these electric charges can interact with one another without even touching each other through what is known as electric fields. Gauss' law helps us to relate the flow of electric field through a given closed surface to the charge enclosed by the surface. For example, you have two hollow cubes with the same size. The first cube you put one positive charge and the second cube you put two positive charges. Clearly, the second cube has a greater electric field through a given area than the first. We call this flow of electric field as flux. Gauss' law tells us that net electric flux through a given closed surface equals the charge enclosed divided by permittivity. The word enclosed because if there is no charge enclosed by the surface, then there is zero flux. For instance, you have one hollow cube and then you put one positive electric charge outside of the cube. The net flux through the cube is said to be zero because there is no charge enclosed or inside of the cube. So there's a little bit about Gauss' law. You guys want to know more about Gauss' law? So make sure to stay tuned until the end of the video.
Everyone, so now I'm going to share about the mathematical concept of Gauss's law. My presentation will consist of two subtopics, which is coordinate systems and also how to find area and volume from the coordinate system. So for the Gauss's law, we will focus on spherical coordinate system and also cylindrical coordinate system. And also to find area and volume, we will use the method of double integration and also triple integration. For spherical coordinate system, we have the point of three components, which are r, theta, and also psi. From the Cartesian, we have x, y, z, and we can also convert from Cartesian to spherical or spherical to Cartesian or otherwise, based on this conversion. And for cylindrical coordinate system, we can also convert from Cartesian and cylindrical to cylindrical or from cylindrical to Cartesian. So from these two slides, we can say that we will make use of Cartesian as our reference to convert either from cylindrical to spherical through Cartesian or from spherical to cylindrical also through Cartesian, or we can also convert directly from cylindrical to spherical and spherical to cylindrical, but it is a different method, different formula. We will talk about the differential normal area, which is ds. And for the differential normal area, we will only talk about the cylindrical coordinate system because it is used in the Gauss's law. For the differential normal area, we will have three different components, which are for vector A rho, vector A psi, and also vector AZ. This tree is for three different components. And lastly, we have differential volume dV. So for differential volume, as the Gauss's law use, we will only focus on the spherical coordinate system, but the step is just same as area. But as you can see here, we have dr, d theta, and also d psi. So here we have three component of differential component, three differential component. So to solve the differential volume for any of this, we will use triple integration to eliminate these three differential element. So if you have any problem regarding the differential volume, just remember the differential normal area solution, but you will need to have another integration, because here we have triple, which means 3 times to integrate. So I think that's all from me. Thank you, and Assalamualaikum.
Hi everyone, I'm Sharul. I will explain to you about electric flux and electric flux density. So, what is different between electric flux and electric flux density? Electric flux is the amount of the field through a particular surface. Electric flux density is the amount of the field going through a unit area. So, both of these ideas are very important in field, especially in electromagnetics. So guys, don't go anywhere. I will explain to you more deep after this. Stay tuned guys.
Electric flux in simple terms. Electric flux is the measure of flow of the electric field through a given area. Electric flux is proportional to the number of electric field lines going through a normally perpendicular surface. Okay, this is formula for electric flux. So psi capital E is equal to capital bold E multiplied by capital bold S, equal to capital E and capital S cos theta. So capital E bold is equal to electric field. Capital S bold is the area of the surface. So capital E is the magnitude. So the theta is the angle between the electric field lines and the normal, which is perpendicular to the S. So S is area of the surface. So psi is flux of electric field through a closed cylindrical surface. So what is electric flux density? Electric flux density is a measure of the strength of an electric field generated by a free electric charge, corresponding to the number of electric lines of force passing through a given area. So Gauss's law states that the net flux through any hypothetical closed surface is equal to 1 over epsilon naught, which epsilon naught is vacuum permittivity times the net electric charge within that closed surface. So electric flux density, which is capital D, is related with electric field, which is capital E. So from equation 1, capital D equal to epsilon capital E. Looking at equation 2, capital E is equal to Q1 over 4 pi epsilon capital R squared. And last equation, which is equation 3, is capital D equal to epsilon capital E equal to Q1 over 4 pi capital R squared. So from equation 3, the electric flux density is very similar to the electric field, but does not depend on the material in which we are measuring. It does not depend on the permittivity capital E. Okay, everybody, you must note that the capital D field is a vector field. So, which means that at every point in space, it has a magnitude and direction. The electric flux density has units of coulomb per meter squared. So, we get the equation which is capital D equal to capital Q over 4 pi r squared, and capital E is equal to capital Q over 4 pi epsilon naught epsilon r and r squared. So from all the equation we get it, we can conclude that capital D is equal to epsilon naught multiplied by epsilon r and multiplied with capital E, and the end of the equation we get it is capital E equal to capital D over capital naught epsilon naught multiplied by epsilon r.
Are you okay, guys? Okay, the last part is what is electric flux important. So we can obviously say electric flux has a physical significance. It measures the total charge enclosed inside any arbitrary surface. The more the electric flux is, the more charge must be there inside the surface to produce the needed number of electric field lines. Okay guys, that's all from me. Bye bye.
Hello guys, now I'm going to present the derivation of Gauss's law. As Anno mentioned just now, the Gauss's law can also be defined as the total electric flux through any closed surface equal to the total charge enclosed by the surface. Thus, in the mathematical form, it will be something look like this. And the term on the left represent the total electric flux through a closed surface, and the term on the right represent the total charge enclosed by that closed surface. Now let us take an example. So let's assume that now we have a point charge positive Q and it is enclosed by a surface X. Hence, the total electric flux through this surface X will be the summation of the small flux on the entire surface X. So we can change the total electric flux into an integral form, which is this one, and it represents the summation of small flux on the surface X. Now we are going to introduce a term called D. In the previous section, we know that D is the electric flux density and it has a unit of coulomb per square meter. Hence, when D is multiplied by surface, we can obtain the electric flux. Now let's focus back on our equations. The small flux here now can be defined as the electric flux density multiplied by the small area on the surface X. After rewriting the equation, the Gauss's law now can be written as the surface integral of electric flux density equals to the total charge enclosed by the surface. Later on the application part, we will show you how to use this formula when you have different types of symmetrical charge distribution. Now let us consider a region of continuous charge distribution with varying volume density of charge ρV, and it is a charge per unit volume. In this region, consider a volume V is enclosed by the surface S. Hence, the total charge enclosed by the surface now can be expressed as the volume integral of charge density. If we equate equation 1 and 2, we will get a new equation for Gauss's law, which is the surface integral of electric flux density is equal to the volume integral of charge density. Next, according to the divergence theorem, it states that the surface integral of a vector field over a closed surface is equal to the volume integral of the divergence over the region inside the surface. Therefore, we can transform the surface integral of electric flux density into the volume integral of the divergence of electric flux density. The dot products between the del operator and the electric flux density is the divergence of electric flux density. Hence, by comparing equation 3 and 4, we can easily realize that the volume charge density is the same as the divergence of the electric flux density. So now we know that there is a way to calculate the volume charge density if electric flux density is given. Also, note that the equation 1 and 5 are basically stating the Gauss law in different ways. Equation 1 is the integral form of Gauss law, whereas equation 5 is the differential of Gauss law. But in this presentation, we will just focus on the integral form of Gauss law and we will use it to calculate the electric field or electric flux density from different symmetrical charge distribution. Alright guys, now we have done the derivation part of Gauss law. Now I will pass the time to the next presentation to explain the application of Gauss law. Thank you.
I will explain the application of Gauss's law. There is a total of 4 applications of Gauss's law that we will discuss further. The first application is point charge, second infinite line charge, next infinite sheet of charge, and finally uniformly charged sphere. The first application is point charge. Assume that a point charge Q is positioned at the origin and consider a sphere of radius r that encloses the charge such that it lies at the center of the sphere. It is easy to see that choosing a spherical surface will satisfy a symmetry condition. Thus, a spherical surface is the Gaussian surface. From the symmetry of the situation, the electric flux density is normal to the Gaussian surface, giving D equal to dr vector AR, and counter integration of the spherical surface is equal to 4 pi r squared. By applying the Gauss's law, the charge is equal to dr 4 pi r squared. Thus, the electric field density equal to Q over pi r square vector AR, or electric field intensity equal to Q over 4 mu naught pi r square vector AR. The next application is infinite line charge. Consider an infinite line of uniform charge lies along the z-axis and a cylindrical surface of radius ρ with height L encloses the line charge. Since the cylindrical surface satisfies the symmetry condition, the Gaussian surface for infinite line charge is cylindrical. Vector D is constant and normal to the Gaussian surface, so we can write vector D equal to d rho vector A rho. The counter integration of the surface is equal to 2 pi rho L. And when we apply the Gauss's law, the charge is equal to d rho 2 pi rho L. Thus, we can conclude that the electric flux density equal to rho L over 2 pi rho vector A rho, and electric field intensity equal to rho L over 2 mu naught pi rho A vector A rho. The third application is infinite sheet of charge. We assume the infinite sheet of uniform charge lying on the z equal to 0 plane and a rectangular box encloses the plane. The rectangular box is cut symmetrically by the sheet of charge and has two of its faces at the bottom and at the top, parallel to the sheet. The rectangular box is the Gaussian surface. D is normal to the sheet, giving vector D equal to dz vector Az. When applying Gauss's law, the charge equal to counter integral of vector D dot ds, resulting dz times summation of surface integral surface of top and bottom. Note that d dot ds evaluated on the sides of the box is 0 because d has no components along ax and ay. If the top and bottom area of the box each has area A, rho SA equal to dz times summation of A plus A. Thus, electric flux density equal to rho S over 2 vector AZ and electric field intensity equal to rho S over 2 mu naught vector AZ. The last application is uniformly charged sphere. There will be two situations for this application, which is R lower than A and R more than A. So first we will go for R lower than A. Consider a sphere of the radius with a uniform charge. For the first case, R lower than A, obviously the sphere has a spherical of Gaussian surface. The total charge enclosed by the spherical surface of radius R is equal to rho V times 4 over 3 pi A cube, and the gap flux linkage is dr 4 pi r square. So the gap flux linkage is equal to the charge enclosed, thus resulting the electrical flux density equal to R over 3 rho V vector AR. The next cases for uniformly charged sphere is when R is greater than A. The Gaussian surface is cylindrical surface, as shown in this figure. So by applying Gauss's law, the charge enclosed is equal to rho V times 4 over 3 pi r cube, and the gap flux linkage is equal to dr 4 pi r square. So we equal the gap flux linkage with the charge enclosed, and we will get the electric flux density is equal to A cube over 3r square times rho V vector AR. So from all the application that we have discussed just now, we can conclude that to apply Gauss's law, first we have to identify the spatial symmetry of the charge distribution, and then construct a mathematical closed surface, which is Gaussian surface, which have the same symmetry as the charge distribution, and then evaluate the integral over the Gaussian surface, that is to calculate the flux through the surface. Next, determine the amount of charge enclosed by the Gaussian surface, and finally evaluate the electric field intensity and electric flux of the charge distribution. That's all about the application of Gauss's law.
Now let's talk about the importance of the Gauss law. The Gauss law is actually a statement is correct for any type of closed surface without having a dependency on the size or shape of the object. So which basically means that no matter what is the size of the object or the shape of the object, the Gauss law could be implemented as long as the surface is closed. Now my friend already have covered the basic formula of Gauss law. And in the formula of Gauss law, the Q, which actually represents the charge, is the combination of all the charges. Those are completely enclosed no matter of any position internal to the surface. In the case of the selected surface, there exist both internal and external charges of the electric field. But where the flux is present on the left position is because of the electric charges in both in and out of the selected surface. Now this is the most vital thing. When we have a Gauss law and how we can implement it and how easy it makes it to calculate the electric field. When the system is symmetric, then we can easily calculate the electric field using the Gauss law. Now we discussed about the importance of Gauss law. Now there are some limitations of Gauss law. We cannot apply Gauss law everywhere. It has some limitations. So first of all, the Gauss law first limitation is the charge should be uniformly distributed. And the second, the surface must be closed. And the third limitation is the line charge distribution will be cylindrical. So means that if you want to find the line charge, the distribution will be cylindrical. And now when you are looking for the plane charge distribution, it will be field box, or it could be either cylindrical. The fifth one, the field point must lie on Gaussian surface. It means that the field point cannot be outside of the Gaussian surface. The Gaussian law does not allow that. And lastly, the charge must be inside of the Gaussian surface. It means the charge, it cannot be outside of the Gaussian surface unless it's a selected surface inside the Gaussian surface. Now let's discuss example how the Gaussian law could be applied to find electric field. In the screen now you can see there is an example given. A charge distribution with spherical symmetry has density with certain parameters is given. We are being asked to find the electric field everywhere. So since we know that our system is symmetric, so we can right away apply the Gaussian law. The charge distribution is similar to the symmetric disease. So as we know that our charge equivalent is going to be integral of rho v dv. So now once we integrate it, we get the electric field easily, which is rho naught r squared 4 epsilon naught r a r. For the second condition, we are applying the same method, and when we integrate it respect to d phi, d theta and dr, we get pi p naught r cubed, or we can write it as E electric field is rho naught r cubed 4 epsilon naught r a r. Thank you.
And this is the end of our presentation. So thank you for your listening. I hope to see you guys next time. So goodbye.